Okay,
It's implicit.
yeah, implicit. So we know it's implicit because even if the direction didn't provide those instructions, we know it's implicit because we have multiple y's in the equation. And also we have another procedure we have to go through is what? Yeah, okay, so let's try that. We know ultimately, how many dy dx's will show up in our derivative line? Two, good. Second. Okay, so 63. Okay, so we will start off with product rule. All right, so what's that prime going to be? G function, no changes. Back to F. G prime, what's G prime going to be? But first, what's the derivative?
dy dx.
Yeah, so remember with e to the u, the original function will show up in your derivative. So it's e to the y times dy dx. Okay, so we're done with that first portion.
So
Minus
the function.
Yes, we do. Yeah, because the rule for e to the u is actually the original function times u prime. So it's not just u prime. The original function will show up in your derivative. Okay, for exponential function. Okay, minus plus. Okay, so the calculus is now done, right? Now we're just moving things around to solve for dy dx. Yes.
Why wouldn't you do like the thing where you do natural log of e times the normal thing times the derivative?
Oh, okay. Right. We don't do that because this is base E.
Oh.
And we're dealing with base. If we do this base 2 or base 3, then we'll do that. Now, having said that, it could work even if you did that. So if you did natural log of E times e to the u times u prime, that is fine, but natural log of E is 1. So it's almost that's why we leave it out, because we know natural log of E is just 1. So if you did natural log of E at the beginning, it's not wrong. You're just taking an extra step.
You go over dx here, right? Like minus 10.
Say that again?
Like this is minus 10 plus 3. So minus 10x.
Well, remember, we're finding the derivative of each term.
Okay.
Right. So what's 10x's derivative?
Oh, this is minus 10.
Yeah. And then 3y's derivative is 3 dy dx. Yeah. So we're taking the derivative of every term in our equation. Okay. Everybody good so far? So now we're just rearranging, right? Trying to get our dy dx's together so we can factor that out. So I'm just going to factor dy dx out. from those two terms. And then the non-dy dx terms, I'm just going to move over to the other side. Solve for dy dx. Divide the parentheses over. And there's our derivative. Okay. Any questions with 63? Okay, 64. Again, we have to involve what? Implicit, yep.
Implicit rules.
Actually, do we do product rule here?
No, we don't use the exponents.
Well, yes and no. There is no product rule initially, but then once we get into the derivative of e to the u times u prime, the product rule will show up there. So again, the derivative for e to the u is e to the u times u prime. It's not going to show up initially because there's no variable, there's no other term that's being multiplied with the e. So this will stay the same, but then once you get into u prime, there's no avoiding product rule with the x and y. Okay, so all right, so let's start our derivative process here. E to the xy becomes what?
E to the y.
Well, e to the xy, right? Times, now we can remember, I know maybe it's tempting to want to find the derivative at this stage or to find the derivative of xy, but remember the rule says e to the u, the original function, no changes will show up in your derivative, and then we can work with the xy. Okay, so now times, now we got to do what rule for xy? Product rule, right? Okay, so now we'll do product rule within this portion here. All this is just for the u prime here. This u prime in itself is going to have to involve product rule. So here's the big picture here. Derivative of e to the u equals e to the u times u prime. And because x and y are connected, u prime is going to feel like a lot because we got to go through a whole product rule just to take care of that messy exponent there. Okay, so f prime is times g
X
plus
plus what x
times
dy dt.
good. Right, so we continue our derivative process plus
Plus 2
minus
2 dy dt.
Well, let's find the derivative first. What's the derivative of y squared? 2y. Yeah, so we find the derivative first, and then we attach dy dx.
Also 2y dy dt.
No.
The y doesn't go away.
Not unless it goes away by itself. Now, if it was like y to the first power, or if it was 2y, for instance, the derivative of 2y would be 2 dy dx. So we always find the derivative first, and then we attach dy dx. Equals what? 0. Okay, harder problem, right? Because we have to work on that first portion of it. But now we expected 2 dy dx to show up, and we did see that. So now it's a matter of cleaning up. We do have to resolve the bracket first. I'm going to distribute the e to the xy through. Then we'll have 4 terms. Then we can group the dy dx together. Then we can factor dy dx out. Yes.
Where did the 10 go?
Good question, right? What's the derivative of 10?
Oh, you do that too.
Yeah. Yeah, we also take the derivative of that 10 it doesn't stay. Okay, good. Distribute. All right, so the terms with dy dx, I'm definitely going to keep on the same side, so I can factor that dy dx out.
Does it matter if we put the y after the ex y?
It doesn't matter, but to me, it feels a little bit cleaner to put it out in front, so it doesn't get confused with the exponent, but that's just my preference. Yeah, but okay, is this all I can do, or can I try to cancel out some more here?
You can cancel.
Okay, we can't cancel
Oh,
out.
no, because they're not, it's not delete code.
What's, yeah, it's attached to a plus, it's attached to terms by addition and subtraction. Now, if everything was multiplied, then yes, I can start canceling out, but across addition and subtraction, we gotta be more careful. It's tempting to want to start reducing, right? But we can't do anything past this unless you can somehow find a GCF from both the top and bottom. If you can take out GCF, then the GCF terms can reduce. But here we gotta be careful that we don't try to reduce too far and end up with an answer that's incorrect. No, that's it. Okay.
So what if the two I was in front though? Could you cancel out like the negative twos? Is there like both in the front of the?
You mean if it was negative 2x minus line root of xy?
Yep, like that.
It still can't. It's still attached to it, so it's abstraction. Now, if it was this, if it was for some reason like this.
Then you can.
Yeah, see how there's no additional subtraction? This can go, this can go, this can go.
Everything goes.
Yeah, everything can go pretty much, right? This will be just be -1. So, but that's not the case, right? So we can't, even though it's tempting, right?
We can't do it. Okay, 65. Okay, right, find equation of tangent line. So we're going to go through the same process. We're still going to find the derivative, but we have one additional step to go through. We have to plug in the order pair to get the slope, and then we'll do point slope form and then write the equation of tangent line. So everything in the beginning will feel the same. We're just having to extend the problem a bit. And imagine from here, you're having to plug in a full order pair to get the slope. That's what we have to do for these problems. 65. Okay, we may have seen these problems already, but it's good to just have some additional practice, right? Okay, so again, what's involved here? Product and implicit, good. Product rule, how many times? Twice. Okay, so we gotta go through product rule twice, right? Okay, so f prime. X becomes 1. Okay, g function, no changes. Back to f. Okay, what's g prime gonna be?
U y over t.
What's third of e to the u? Is it just dy dx?
Oh, e y.
Yeah. Yes, the original function first, and then dy dx. Okay, on to the second expression here. Good, dy dx. And then we also see two y's here, right? So we're expecting two dy dx's when everything is said and done. Times g plus y times
Thanks.
E to the x times.
yeah, e to the x times 1, which is just e to the x, right? Equals 0, 0. Right, we did do this problem before because we talked about how we could solve for dy dx, but it's not asking for the equation. It's just asking for the tangent line. So let's just go ahead and replace every x and y with 0 and 1. We can solve for dy dx a lot faster. And when we solve for dy dx, once we plug in 0 and 1, that's going to be our slope value. Okay, so every x gets replaced with 0, every y gets replaced with 1. Now, anything times 0 is going to be 0, so that cleans up this for us. But anything raised to 0 is equal to what? It's equal to 1. Good. So e to the 0 goes away, but the number in front is going to have to stay here. So e plus dy dx plus 1 is equal to 0. So I'm going to solve for dy dx, and that's going to lead me to my slope. So dy dx is simply negative e minus 1. Okay, I'm asking to find the tangent line equation. So let's gather some, make sure we have our information all set up here. Order pair is 0, 1. And now point slope 1. Mm-hmm.
How come the first like 1 equal 1
Because e to the first power is just going to be e, right? Now, if it was 0 times e to the first power, then it'll go away. It'll be 0. Yeah. If the exponent is 0.
No, the point is 0, 1, so why would
Oh, sorry. You're x minus 0. Sorry. Okay. Yeah. Okay, everybody good? Yeah. Okay, let's try one more here. One more on this page here, 66. This is also a tangent line equation 1.
Example.
Okay, good.
You should do product rule.
Okay, let's talk through this problem a bit. First, do you see the need for implicit? Yes, yeah. You see y's mixed into the equation. That's good. You've mentioned product rule, which we could do, but this is a natural log expression. We have some options available to us here. What can we do before our derivative process? We can expand, right? Remember, natural log of AB can be expanded. I mean, if you didn't expand, you can still find the derivative, but it'll make things a lot easier if we can split this up into separate problems. Right? Okay. Now, we couldn't do that with e to the xy. All right, we couldn't do that here, but we can do that here. Okay, so let's take that cleanup step initially before we consider our derivative step.
Both those elements.
Ln x plus ln y. Can't do anything here, so I mean we could make it e to the x over e to the y, but I don't know if that makes it any easier, so we'll leave it in this form. Okay, so now everything is just a derivative rule. No product rule you have to worry about. Right, so now, but we do have to do implicit. We do have to keep track of our dy dx's. Okay, so one term at a time. 1 becomes 0. Natural log of x. Thank you. Okay, natural log of y becomes good. Okay, e to the u becomes e to the u times u prime. So let's go through that process. E to the u. So e to the xy starts off with, sorry, e to the x minus y starts off with, yeah, the original problem will show up in your derivative times, well, good. So we got to find the derivative of my exponent. My derivative, these are just separate terms, so we can take each derivative separately. X becomes 1, y becomes good, 1 dy. Good, yeah. So I can have a 1 there, or I can leave it out, but okay.
We don't have to spread out the thing like you do in the multiplication. You don't have to do the product.
You're right. So why do we have to do product rule here with all that messiness, but not here? Right, because the terms are not being multiplied, right? We do product rule if terms are being multiplied, but if terms are added and subtracted, then they're independent. We can treat them separately and not have to go through a messy process. Okay, is this asking for the derivative equation? No, so we could take a little bit of a shortcut in terms of we don't have to keep track of all of our x's and y's and solve for dy dx. I mean, we still solve for dy dx, but let's just speed up that process and replace all the x's and y's with 1 and 1, and that will get us to our slope a little faster, rather than having to rearrange everything, get dy dx, and then plug in 1 and 1. We can jump to that step a little earlier here. So every x and y gets replaced with 1. Okay, so I get 1 plus 1 dy dx. Actually, I do like having that 1 in front. It helps us later on if we're trying to add like terms, that having that number there is helpful. Equals what? E to the 0, right? Which is 1. Okay, so I'll put e to the 0, but we know it's going to turn into a 1. Okay, so I can drop this out, right? That's going to go away. So I have 1 plus 1 dy dx. Notice all the x's and y's are gone, so when we solve for dy dx, we're actually arriving at the actual slope value. Okay, combine some like terms here. If I add that 1 dy dx over, I get 2 dy dx. Yes, that's right. But if I distribute a 1 through, nothing changes, right? So 1 times 1 is 1. 1 times 1 dy dx is still negative 1 dy dx. So I get 2 dy dx equals 0. So what's my slope? 0 over 2, which is 0, right? Right, we can still write an equation of tangent line. It's just it's going to look a lot simpler now that my slope is 0. You can leave it like this, or you can clean it all the way up to just say y equals 1, but that's fine if you don't reduce. Okay, good questions. What's anything else that you guys have questions about? You know, it's a lot, but it's good to, if something doesn't seem right or something doesn't quite click, I can,
He's like, what happens to that new idx on the right? Where did you show even 0 you want?
over here.
Yeah.
So I added this over to the left side to combine like terms. So this becomes a plus 1 dy dx, right? What's 1 dy dx plus 1 dy dx? 2 dy dx.
Oh, you wanted it?
Yes, I can add, they're like terms, right?
Yeah.
So imagine dy dx is just a variable. It's just a derivative variable. It's like 1y equals negative 1y. So treat dy dx like its own variable.
And why is it minus 1 dy dx when you like solve for the derivative? Like, what happens to like the y?
Right, so what's the derivative of x? 1. Okay, what's the derivative of y? Times dy dx. So that's why it's negative 1 dy dx.
And you can take like you don't have to like put actually write the negative 1, you just put minus dy dx.
You can. Actually, I do like having that minus 1 now I think about it, because having that negative 1 there helps us see that, oh, I can just add like terms, right? Having that 1 and 1 is helpful, I think. You don't have to, but it is nice to see some numbers in front to help you add those like terms.
Just so why part of the answer? So, answer to y equals 1.
Right, well, it's asking for tangent line equations. So once we get our slope, we just take our slope and our point and put in the point slope form. So this is the answer, but because 0 wipes out this whole right side, I can clean it up even further and say y equals 1, but you can leave it in either form. Okay. All right. Okay, so page 23. Let's see, your packet has a blank page on the back, right? Okay, so I want us to practice the new rules. So at the very back of your packet, I want us to do this every day leading up to the quiz, just so that we can have that practice of memorizing these rules. Okay, so I just want to show that these 4 rules is really just an extension of the top 2, right? So leave it as it is. Don't write anything down yet. Let me go through the rules first, and then I'm going to erase it, and then you guys can try it. Okay. And we'll do this every day leading up to the quiz. Okay. What's the derivative for natural log of u? You remember. U prime over u. So if you can build that natural log, then it's going to look very similar with log base a, right? Other bases is still going to have that u prime over u, but there's going to be a 1 in front. Natural log of a. Right, but it's going to be in its denominator, 1 over natural log of a. There's going to be a coefficient. It's going to be a conversion that has to occur before that u prime over u, because it's not base e. All right, we did this a lot, right? What's the derivative of e to the u? Right? So what you did was you wrote down the original problem and you multiplied by the exponent's derivative. So a to the u, like 2 to the u, or 2 to the x, or 3 to the x, any of the bases that are exponential, we still do the same process, right? The original function will show up just like above. times exponent derivative, but natural log of A. And some students have trouble remembering where that natural log of A goes. Is it in the numerator or is it in the denominator? Again, what I do is I look at the rest of my derivative. If I don't see any denominator present, then I know my natural log of A is in the numerator. Here, I do have some denominator presence with my derivative, so that reminds me, okay, my natural log of A is in the denominator. Okay, let me erase this and have you guys try it, okay?
You want to do that?
I just want you to write down the derivatives.
Oh.
Or see if you can recall them from memory. Okay, let's check our derivative rule. Okay, and we'll do this every day until we get comfortable. I think by end of next week, we should be really good with these rules, right?
These are 4 main ones. Because
Yeah, these are the 4 main ones that that you'll be responsible for on next week's.
So I know log properties start.
Yeah, and also right log properties. Okay, let's go to page 23. All right, we have natural log expression with a lot of messiness there. We are asked to find the derivative, but is there anything that we can do before our derivative begins? Quotient. Yeah. So natural log of A over B can be expanded into natural log of A minus natural log of B. Try that step first.
Will you give us a packet for
I'm sorry.
Will you give us another packet for?
Yes, yeah, I will. I'll go give it out today, but I figured there's enough for us to practice today. I'll give you a review packet Monday, Wednesday, and Thursday. Yeah, I'll give you 3 review packets. And next week's assessment will just be a quiz. We just do a quiz over this unit, no test.
It's
Right,
Monday.
election day, so no school Tuesday. Okay, so natural log of A minus natural log of B. And I also rewrote the radical as a rational exponent, but we can keep making this simpler for our derivative process, right? What else can we do? Yeah, move the exponents in front, right? So anytime we see a log or natural log problem, we always want to see if we can make life easier on us so that we're not having to deal with a really messy derivative, right? So now the derivative should feel a lot more manageable, which is a simple u prime over u.
no calculus yet, but now the calculus should feel easier. Now we'll do 5 is going to stay, then u prime over u, and then the 1/4 will stay, and then u prime over u. Okay, no need to find common denominator. You can leave your answer unsimplified or in separate denominators, but try to clean up within each individual fraction. Okay. Number 2, I know number 2 looks more intimidating because it's not natural log, but we can still do all the same things that we did for number 1, right? We can still apply log properties. So pretend like you're dealing with a natural log problem, and then at the very end, you just have to make an adjustment with that base 3. So what would you do first?
And,
Okay, what's your first expansion property you would do?
Log of -6.
You could, but maybe something that we can do before the quotient property. Yeah, let's bring that 3 down first. I mean, if you did natural log of, or if you did log of a minus log of b, you'll have to make sure that 3 exponent stays with each term. I think bringing that 3 down makes it a little bit cleaner. The only thing you have to worry about is if you bring that 3 down and then you do log quotient property, that 3 has to distribute to both terms. So just make sure you got to keep track of that coefficient for both your log terms. Okay. I know this is not a natural log, but you're still gonna keep the coefficient. You're still gonna do a u prime over u. Be a little bit of conversion in front, and that conversion will be what? 1 over natural log of 3. Yeah, so 1 over natural log of 3 was gonna be part of your coefficient answer, and over here as well. But then I just want us to not feel like we're dealing with a brand new rule here. It's just an extension of the natural log rule with a little bit of adjustment in front.
I'm a little confused on like since the rule says like log of a,
Log base a of u, yeah.
oh, so it'd be, okay, never mind.
So my a is 3, and then
So,
the u
but
is
what
the
if
frequency.
Just the normal natural.
It'll be normal natural log if you see ln. So ln is a shorthand way of saying, yeah, it's a shorthand way of saying log base e of I know it's not a problem, but instead of writing log base e, the problem is always going to show you ln, but these are the same thing. So this is a shorthand way of saying log base e. Okay, you can present your answers a number of different ways. You put it all into one fraction. Let's try to clean up within each individual fraction. I'm not going to be too picky about the log. Should be 3, right?
Can that not cancel
Uh,
out?
no, we can't. Why can't we not cancel these 3s out?
Natural log.
Yeah, the 3 is inside the natural log. It's not a standalone term. If it was 3 natural log, then the 3 in front we cancel out, but that 3 is inside, so it's not the same thing as the 3 above.
Well, you take what's off if you don't simplify.
No, I won't. I probably won't. Yeah. I'm more concerned about, can you actually get to the derivative? You know, anything after that.
What does that box description say for the day?
It's just a reminder of derivative rule.
Oh, where'd you get the 16?
Do that. Should be 8x cubed, right? Okay, thanks for checking the work there. Okay, number 3. X e to the 2 minus x squared. What do you see here? Product rule, yeah. This is not a natural log expansion problem. This is x times e to the 2 minus x squared. We just have to jump directly into product rule, right? F prime g plus f g prime. F prime, x becomes 1, g is just e to the 2 minus x squared, plus f is x, and then the derivative for e to the 2 minus x squared is the original function times the exponent's derivative. Yeah, you don't have to do this step here. I factored it out, but I'm not going to be picky about how you clean up your answer.
What about you had the right answer, but then you factored wrong again, would you?
Yeah, I may take off a point, so maybe it's a safer to just bigger answer. Yeah, so that's a good strategy too. On the AP exam, if it's free response, you almost never want to clean up, right? Because if you clean up incorrectly, you're inviting them to take off points, right? So it's almost better to just leave your answer unsimplified.
So if we leave it like it is up on the top, you want to take off points?
No.
Okay.
Okay, number 4, what can we do first? Expand, right? So log base 5, natural log, they all have the same property. You can expand that.
Numerator myself.
Yep.
For myself.
Right. There's no exponent that's getting in the way, so we can jump directly into expanding. But if there was an exponent outside the entire parentheses, I would do that first, and then I would expand. Okay, we'll finish up this problem, this page on Monday. I'll give you guys a quiz review on Monday. We'll have Monday, Wednesday, and Thursday to review. Your quiz will be on Friday. Okay. No homework on the weekend.
It's kind of.
You can leave it like this. This is fine. I just immerse it into a bigger branch. Okay, great. Thank you.
And then my pass should be.
Yep, I saw it. Thank you. Okay, great. Thank you.
Schedule say what's off, what they're missing to say, so.
Monday, you want to do the like?
Doing what?
Oh, yeah, you can do the
derivative.
Okay.
These things were not completed.
Don't you put
Friday.
Friday?
It's Friday.
Free to go. Because I was watching the other one, how it's even, it goes.
Did you change the natural log?
So now.
Why are we talking about it?
He was then to take it all, and since then.
Well, remember, what's the derivative of log base A of U? If the one over natural log A.
Okay.
So we're just doing the,
That one, okay.
oh, sorry, we're just doing this rule here.
Okay,
Yeah.
I just gotta memorize that.
Yeah, you gotta memorize it, yeah. It's basically,
But now.
it's U prime over U with a little bit extra.
Okay. What the Bills win Sunday night?
Who they're playing?
Bengals. Oh, that's right. Bengals. Yeah, thank you. You're kind of crap talking us too, like, you're creating these fake storylines.
Oh,
Like that, like, when they beat it, like, when they beat us in the playoffs, like that, like you're saying that our players said it, but we would have won it with from snow. I mean, I don't know. But like, because they know that we're gonna come into the game with like extra emotion because we lost.
Oh.
They're trying to create these storylines.
I think it's for.
That makes sense. Now I can coordinate stuff. Things are just even to grow, not they wait.
You could mention. Yeah, that was great. That was actually. Thank you, Mr. Guy. Yeah, third period.
Not really. Good morning. You guys. There's like every. Oh my God.